We've been looking at derivatives to help us graph, to find where a graph is increasing, where a graph is decreasing, to find maximum and minimum values if they occur. Now we're going to look at using the derivative, the second derivative, to show us concavity. How fast is that growth rate growing or decreasing? And that's what the second derivative is going to tell us what to do. So let's first look at notation for higher derivatives. We've been just looking at taking the first derivative, but if we take the second derivative, that's just the derivative of the first derivative. The third derivative would be the derivative of the second derivative. But notation for higher derivatives, well, it depends on which notation you're using. But if we're using that prime, so y double prime, that would be representing, or f double prime of x is one way to write the second derivative. Another way to write it, though, is d squared y all over dx squared. And here's another one your book uses, but I haven't used in this class, that capital D quantity squared of x, f of x. But these are all just notation of saying that we're looking at the second derivative of our function. We can go and extend this further. So this is for the second derivative. So if I wanted to take the fourth derivative, I would have 4 primes in here of x. Or d to the fourth y, dx to the fourth. Okay, so let's just start first by looking at higher derivatives, and then we'll go into the graphs and what that looks like. Let me pull up an example. So it says find the second derivative for each function, and then find the second derivative at 0 and the second derivative at 2. And so let's look at, how about f of x equals eight x squared plus 6x plus 5. So we want to find the second derivative, so f double prime of x. We want to find the second derivative at 0, so f double prime is 0. And the second derivative at 2, so f double prime of 2. So this isn't bad, right? This one, when we're taking the derivative, it's just the polynomial, just using that general power rule. So taking the derivative of the first term, 8x squared, bringing down our power, 2 times that coefficient of 8, that gives us 16. Subtract 1 from our power, so we get 16x. Plus the derivative of 6x, well, that's just 6, and the derivative of constant is 0. So that's our first derivative. Our second derivative of 16x is 16, and the derivative of a constant 6 is 0. So we found what the second derivative is, but notice that there's no value of x left in there when we found the second derivative. So when we go back in and we plug in a number wherever we see x, well, there's no x. So we're just going to get back 16. So the double derivative of f at 0 is 16, and the double derivative at 2 is also 16. Okay, if there was a variable x left in there, then we would plug those numbers in and simplified. So that tells me right here that my second derivative is always positive. And we're going to be looking at when our second derivative is a positive and when it's negative. And that, again, will tell us about some concavity, and I'll talk about that again in a minute. But let's, again, take a look at a couple more examples of finding higher derivatives. What if we had f of x was equal to negative x all over 1 minus x squared? And again, we want to find the second derivative, and we want to evaluate that at 0 and 2. So same directions as above. So this is a little more complicated to take the derivative, right? Because we need to use the quotient rule. So just recall, if you have y is equal to some p over q, when we look at the derivative using the quotient rule, we're taking the derivative of the top times the bottom minus the top times the derivative of the bottom all over that bottom quantity squared. Okay, so using that quotient rule, taking the derivative of our numerator is -1, all times our denominator, so put parentheses around that whole thing, 1 minus x squared, minus my numerator, which is -x, times the derivative of this denominator, and the derivative of that denominator is -2x. Put this all over that denominator, which is 1 minus x quantity squared, that quantity squared. So let's clean this up before we take the second derivative. Let's distribute in the numerator and combine like terms where necessary. So distributing that -1, we get -1 plus x squared. So I notice here we got multiple negatives, and it's all multiplication. So a negative right in here times a negative in here, that's positive, times another negative, that's negative. So this is going to be a minus. And then an x times a 2x is a 2x squared. All over this denominator quantity squared. I think I'm going to keep it factored form for the denominator. So combine like terms in the numerator, x squared minus 2x squared is a -1x squared or -x squared. And then we have that -1 all over our denominator, 1 minus x squared quantity squared. Okay, so that's the first derivative. So finding the second derivative, let's just move this up. So to find the second derivative, again, we're going to have to use that quotient rule. So quotient rule says the derivative of our numerator, so derivative of that numerator, derivative of -x squared is -2x. Derivative of that constant is 0, times the denominator, 1 minus x squared quantity squared, minus the numerator, that parentheses around -x squared minus 1, times the derivative of the denominator. Okay, so we need to use the chain rule here. So our outer function is this quantity squared. So using the chain rule, bring down our power, taking the derivative of the outer. So this would be 2 of the inner, 1 minus x squared. Subtract one exponent from the outer function. So that's 1 times the derivative of this inner piece. So the derivative of the inner piece is -2x. All over the denominator, 1 minus x squared, squared, but then this also has to be quantity squared. So I want to clean this up. I could distribute, but I would first have to FOIL out this 1 minus x squared quantity squared. But instead of doing that, let's this will help us factor anyways. Notice that we have one of them here. Well, we have 2 of them there. and we have one of them here. So we can actually pull out one of those factors. So we can pull out a 1 minus x squared from this grouping and from this grouping. Let's see. I also notice they both have a minus 2x in common, right? We have a minus 2x in here, and we have a minus 2x in here. So let's also pull that out and put it out in front. So if we pulled out a negative 2x and a factor of 1 minus x squared from this first piece, all you're left with is one of those factors, 1 minus x squared. So that was for the first grouping. For the second grouping, we have this minus sign. Well, we pulled out one of these and one of these. So we have to look at what's left. We're left with that 2. And then a parentheses, I'm going to write the parentheses, negative x squared minus 1. All over this denominator. Well, rules of exponents, powers to powers, power to power, we multiply. So this is the same thing as 1 minus x squared, that quantity to the 4th power. Okay. So notice you have 1 minus x squared here, and you have 4 of them here. So if we can't cancel one of them with the one on top, that will now make it 3 of them. And then let's clean up our numerator a little bit. So let's distribute this negative 2 inside this parentheses, and then we'll start combining like terms. So we have this negative 2x. And then we have 1 minus x squared. Distributing that negative 2 times negative x squared, that's plus 2x squared. And negative 2 times negative 1 gives us that plus 2. All over this 1 minus x squared quantity cubed. So inside that bracket, we can combine like terms. We have a 2x squared minus a 1x squared, so that's just an x squared. And we have this 1 plus 2, so that gives me plus 3. All over 1 minus x squared quantity cubed. Okay, so we found the second derivative. And they wanted us to also evaluate the second derivative at 0. So all we're doing, go back in wherever you see an x in the second derivative, we're going to replace it with 0. So this would give us, well, negative 2 times 0, all times 0 squared plus 3. All over 1 minus 0 squared, and that quantity is cubed. Well, notice that numerator, negative 2 times 0 is 0, and 0 times that bracket, that's going to give us back 0. So we have 0 in the numerator, which is okay, as long as we don't have 0 in the denominator. In the denominator, we have really just the 1 left in that parentheses, and cubed is 1. So this is equal to 0. So the double derivative evaluated at 0 is 0. And now look at the double derivative of double prime evaluated when x is 2. So going in here, wherever we see an x, we're going to replace it with a 2. So we have negative 2 all times parentheses 2. We have 2 squared plus 3 all over 1 minus 2 squared, and that quantity is cubed. So simplify, -2 times +2 is -4, all times in our bracket. So 2 squared is 4 plus that 3. So inside that bracket, we're going to get a 7. All over, first do exponent. So that 2 squared is 4. So 1 minus 4 is -3. Maybe I'll just write it for now. -3 quantity cubed. So -4 times 7 is -28. And if you cube -3, you get back -27. So it depends on if they want you to leave this as a improper fraction or write it as a mixed number. But 2 negatives division is positive. So this is equal to 28 over 27, or the same thing as 1 and 1/27. So here's a case where we had to take the second derivative, but there was a lot more work than that first one, right? Because we had to use the quotient rule twice. And within the second one, we had to use the chain rule. Okay, so in this example, we have f of x equals 1/2 times e raised to that x squared power. So again, we want to find the double derivative, and the double derivative evaluated at 0 and 2. So first thing we need to do is take the derivative of f of x, but let's just review real quick, just in case you forgot. If you had, let's say, g of x equals e raised to some function h of x, recall when we take the derivative of e, we take the derivative of the exponent times the original e itself. So times e raised, in this case, to the hx power. So taking the derivative of f of x, we're going to keep that 1/2 there. We're taking the derivative of our exponent. So derivative of x squared is 2x, all times the original e. So all times e to the x squared. So let's clean it up before we take the second derivative. Well, 1/2 times 2x. 2's cancel that there, and we're just left with x times e to the x squared. So now when we take the derivative of the derivative, notice that we now have to apply the product rule. And maybe we need to write that down. So let's say you have y is equal to some function f times g. The product rule said y prime, derivative of the first times the second, plus the first times the derivative of the second. So y prime is f prime equal to f prime times g plus f times g prime. So the second derivative, we're looking at the derivative of the first. So derivative of x is 1. All times the second, which was our e to the x squared, plus the first, which is x, times the derivative of the second. So the derivative of e to the x squared. So derivative of our exponent, derivative of our x squared is 2x, times the original e to the x squared power. So this is e to the x squared power plus, well, x times 2x is 2x squared, e to the x squared power. So now to evaluate that second derivative at 0. So going into our second derivative, wherever we see an x, we're going to plug in 0. So this is equal to e raised to the 0, and that 0 squared, plus 2 times 0 squared, and then e raised to the 0 squared. Well, a number other than 0 that is raised to the 0 is always 1. So we're using the fact that d raised to the 0 is 1, as long as b is not 0 itself. So e raised to the 0 power, because 0 squared is 0. So e raised to the 0 power, that's just 1. Plus, well, 2 times 0 is 0, and 0 times this e to the 0, which is 1, is just 0. So the double derivative evaluated at 0 gives us back 1. And now we want to look at this by finding the double derivative evaluated when x is 2. So looking at our double derivative, now we're going to plug in 2 wherever we see an x. So we have e raised to the 2 squared plus 2 times 2 squared times e raised to the 2 squared. Just going to get rid of this. Okay, so simplifying this down, this is e raised to the 4th power plus, well, 2 squared is 4 times this 2 out front, that's going to give me 8, e raised to the 4th power. Notice that these are like terms. Back here, at our first derivative, they weren't like terms because one had an x squared in there. This one did not have an x, but these are like terms. They both have an e to the 4th. So we're taking 1 e to the 4th plus 8 e to the 4th, and that will give us 9 e to the 4th power. My guess is you're asked to leave this in exact form, and so you won't have to go and evaluate what e is in the calculator and raise that to the 4th. Okay, so let's look at one more, this time with natural log involved in it, and then we'll talk about concavity and finding that. So the next example, we have the function f of x is equal to the natural log of x, and then plus 1 over x. So we're finding the double derivative evaluated at 0, and double derivative evaluated at 2. So again, let's just kind of review. If you had y is equal to the natural log of, maybe it was not just x, some function g of x. Remember, when we take the derivative, this is equal to 1 over what you're taking the natural log of, which is g of x in this case, times the derivative of the inside, so g prime of x. So when we had y is equal to the natural log of x, if we apply that rule, recall that this is just 1 over what you're taking the natural log of, which is x, and the derivative of x is just 1. So derivative of natural log of x was 1 over x. Before we take the derivative of f of x, I think it would be easier if we rewrite this a little bit. So natural log of x plus, instead of 1 over x, let's rewrite that as x raised to the negative 1 power. That way we don't have to worry about using the quotient rule to take the derivative of that piece. So taking the first derivative of f of x, derivative of natural log of x, well, that was 1 over x, plus the derivative of x to the negative 1 power is negative 1 times x to the negative 2 power. So let's rewrite this first derivative a little bit before we take the second derivative. So we can rewrite this 1 over x as x to the negative 1 power. And then the second piece is minus x to the negative 2 power. So taking the second derivative, so derivative of the first derivative, derivative of x to the negative 1 power is negative x to the negative 2 power, minus, and derivative of x to the negative 2 power, bring down the power, so negative 2x, subtract 1 from the power, negative 3. So this is really negative 1 over x squared, just rewriting that piece to have a positive exponent, plus 2 negative is positive, 2 over x cubed. I can leave it like this, or I can rewrite this as a single fraction by getting a common denominator. Now we just want to evaluate the second derivative. We're going to have a problem though when we're evaluating this at 0. Notice that that would give us 0 in the denominator. That would give us negative 1 over 0 squared, which is 0, plus 2 over 0. This is undefined. So the derivative, second derivative at 0 is undefined. The second derivative, though, evaluated at 2, this would equal negative 1 all over this 2 squared plus 2 all over 2 cubed. So we get negative 1 over 4, 2 squared is 4, plus 2 all over 2 cubed is 8. So this is negative 1/4. Notice that 2/8 though reduces down to positive 1/4. So negative 1/4 plus 1/4 gives us 0. So the double derivative evaluated at 2 is equal to 0.